What if I told you that you could solve some really complex problems? Not with a bunch of numbers, but just by looking at a picture. Well, today, that's exactly what we're doing. We're going to explore the power of the graphical solution to find one very, very special spot, the point where two paths cross. All right, let's bring this down to earth. Imagine you're running a business, right? You've got costs, all the money going out, and you've got sales, all the money coming in. The biggest question you're always asking is, when do you finally break even? When does the money you're making finally catch up to the money you're spending? Well, believe it or not, the answer to that huge question is hiding right here on this graph from a factory. Now, I know it might look like a jumble of lines and numbers, but the entire answer, the key to knowing if you're profitably or not, is hidden in just one single point. And our job today is to find it. Okay, so before we can solve that factory problem, we gotta get a handle on our main tool. Let's explore the incredible power of a single point and see how it can unravel a really complex problem. And it all kicks off with this one fundamental building block, the linear equation. We're about to turn some abstract algebra into something you can actually see, a simple visual path. So what even is a linear equation? Look, don't let the name scare you. In simple terms, it's just a rule that connects two things, usually x and y. But here's the real key, the part you need to remember. When you plot an equation like this on a graph, it always creates a perfectly straight line. Every single time. It's a totally predictable path. Okay, so how do you actually get that line on paper? Well, it's actually a pretty simple recipe. First, you just shuffle the equation around to get x or y by itself. Then, you plug in a few numbers to find some points that work. We say at least 3 just to be safe. You pop those pairs of values into a neat little table. Then, you plot those points on your graph. And for the final step, you just connect the dots. That's it. You've officially turned an equation into a line. And check this out. This slide shows you exactly what I mean. On the left, you just have a table of values. It's just numbers, right? But on the right, you can see how each of those number pairs becomes a specific dot on the graph. And when you connect them, bam, you've got your line. It's a visual path of every single possible answer to that one equation. All right, so one line is cool, right? But the real magic, the really interesting stuff happens when we throw a second line into the mix, a whole other path. This is where we start finding that one special answer that works for two different problems at the same time. Think about it for a second. That single line we just drew, it actually represents an infinite number of possible solutions. Any point, anywhere on that line, is a totally valid answer for that one equation. It's like a whole universe of possibilities. But here's the puzzle. What if you have to follow two different rules at the same time? Let's say you have this first equation, 3x minus 2y equals 4. And then you have a second one, 5x minus 2y equals 0. Each one of these is going to create its own unique line with its own infinite set of answers. So here's the million-dollar question. What single point, what specific pair of x and y values can possibly make both of those equations true at the exact same time? And boom, here it is. This is the big aha moment. The answer is just so beautifully simple. As the source material tells us, the solution is just the coordinates of the point of intersection. That's it. The answer isn't some crazy, complicated calculation. It's just the one place where the two paths cross. All right, enough theory. Let's get our hands dirty and actually put this into practice. Let's solve a problem just by seeing the answer. Okay, so we're taking those two equations from before, and we're going to do the exact same thing we learned for each one. We make a table of values for that first equation, 3x minus 2y equals 4, and then we do it all over again for the second one, 5x minus 2y equals 0. We're just getting our coordinates lined up and ready to go. And look at this. This is a perfect picture of what we're talking about. We take the points from both of our tables and we plot them on the same graph. We draw the first line, then we draw the second line, and now all we have to do is look. See where they meet? That single point, the one labeled P right there, that's our answer. It's that simple. So what are the coordinates of that point? Well, the solution is point P at -2, -5. And what that means is that x equals -2 and y equals -5 is the one and only pair of values in the entire universe that makes both of our original equations true. And we found it just by seeing where two lines crossed. Pretty cool. Awesome. So now that we've got the skills, we can finally go all the way back to the beginning, back to that factory floor, and figure out their break-even problem once and for all. So here's that graph again. It's actually pretty simple when you break it down. That line labeled CP, that's the cost price. It shows how much money the factory spends to make its products. You can see the more stuff they make, the higher the cost goes. And the SP line, that's the selling price. It shows how much money they're bringing in from sales. The more they sell, the more money comes in.
And you guessed it, just like in our last example, these two lines cross at one single spot. As our source points out, at this point of intersection, the cost price is the same as the selling price. This is literally the definition of breaking even. All the money you spent is now exactly equal to all the money you've brought in. You're not making a profit yet, but crucially, you're not losing money either.
So, what's the number? What's the answer? We just look at the graph, find where they cross, and trace it down to the axis for the number of articles. And the answer is 40. The factory has to make and sell exactly 40 items to break even. If they sell 39, they're losing money. If they sell 41, they're finally in the black. So let's do a quick recap of the big ideas here. First, any line on a graph shows you every possible solution for its one equation. Second, the spot where two lines intersect, that's the single unique solution that works for both equations. And most importantly, this isn't just some abstract math exercise. This visual method can solve real-world problems. Finding where paths cross is an incredibly powerful tool. And that kind of leaves us with one final question to chew on. We use this whole idea to find a business's break-even point. But what other real-world problems do you think could be solved just by finding where two paths cross? Maybe it's comparing two different cell phone plans to see which one is cheaper in the long run, or figuring out the exact moment when one investment is going to outperform another. The possibilities you'll find are absolutely